First of all, let me start by thanking all of you for having me here. And I particularly want to thank the student volunteers who have helped make this happen. I really appreciate your time and effort. And thank you all for attending. Okay, so, and like it was mentioned, my name is Harish Ravichandar. I'm at Georgia Tech. So I was thinking about, when I said, yes, I will give a seminar, I was thinking about what to talk about. So let me start with this. I'm going to start with a high-level idea of what our lab does, if this clicker works. Maybe it is, and it's just not pointing the right way. Yeah. So let me start with the high-level goal of what we do in our lab. So our overall goal is to enable reliable and collaborative robots. The idea is to have robots learn to reliably operate in difficult environments. And by difficult, I mean environments where things dynamically change and are highly unstructured and potentially have humans in the mix, right? So in dynamic, unstructured human environments. So that's our overarching. So you can ask the question of what's the point of going towards those kinds of techniques and having robots being able to do those things? Turns out these kinds of settings appear in a variety of different domains and applications. You can think anywhere from manufacturing, defense, assistive robotics, or even autonomous driving for that matter. In many of these domains, you have these kinds of requirements of robots that are very reliable and robots that can collaborate. But you can also ask the question of what's so hard about these challenges and what are the core challenges that we tend to focus on and solve, right? So there are many challenges here, including things like task variability, because you can't really specify just one task and expect your robot to always experience those kinds of tasks. There is variability. Of course, there is inherently uncertainty. There is sparse data. We unfortunately do not have access to the ridiculous amount of data. Some might push back on that. I will talk about that in just a bit. There are safety constraints we have to worry about. And there is, of course, preferences. And of course, I don't have to tell you, sometimes humans are not very easy to deal with. So we have to also take them into account. So what do we really want from robots if we want them to succeed in these kinds of settings? So I'm going to argue you need three things. And one thing I want to specify is that these three things are, in my opinion, necessary but not sufficient. Of course, robotics needs a lot more things and it's inherently multifaceted. So these solutions I'm going to talk about today are not going to completely solve it, but these are essential elements that we focus on. The first one is reliability. What I mean by reliability is that we want the robots that we deploy in the real world to be able to operate in a way that we predict and in a way that we expect. We want to be able to say something about, this is what my robot would do. So we are very interested in reliability, and reliability can be thought of as it should be able to generalize and handle new variations, and also you might be able to provide guarantees and predictability to the policies you're running. The second one is adaptation. Because inherently, the robot is going to experience things that it's not seen before, right? From a machine learning perspective, this could be things like your out-of-distribution problems. Or from a more classical perspective, this could be things like your disturbances and changes in conditions that you have to be either resilient to or robust to. And the third one is coordination. This is primarily motivated by the fact that no single robot is going to accomplish everything that you want accomplished. And if we want robots to succeed in complex settings, inevitably they have to work together. Not just robots working with themselves, but robots have to work with other people as well. This is where we explicitly focus and embrace heterogeneity. By heterogeneity, I mean different agents in your system are differently capable. How do you effectively incentivize coordination in these kinds of settings where you have heterogeneous agents? So these are the sort of the three pieces of the puzzle that we focus on. So of course, some of you might be thinking or asking, who cares? I'm just going to fine tune a foundation model. That's going to solve all my problems. Why do I have to worry about these kinds of methods? So there are a couple of things I want to say about that. One thing is there are practical limitations with these kinds of approaches that people often don't talk about. One is they tend to be extremely resource heavy. Resources, both in terms of data, but also in terms of compute. Not everybody has access to those kinds of things. And despite the advances we are seeing, it's not yet clear how widely applicable and useful these would be. The second one, which is even more important in my opinion, is that most of these methods require expert tuning. So often one criticism you hear about manually designed controllers, for example, in robotics, is that it requires expertise from humans to be able to design these things. Every time you have a new task, somebody has to design your controller, and that tends to be the criticism of those methods. And then usually what is presented as a solution is, here is a learning-based method that's where you don't have to tune a controller. But what often doesn't get talked about is you have just replaced one set of hyperparameters for a different one. It's not like learning-based solutions, you can just throw them out there in the real world and it works. Somebody has to really tune several hyperparameters associated with these learning frameworks. So that's an important limitation as well. And the third one is they are inscrutable, meaning they tend to be black boxes more or less, which means you have a very little ability to truly understand and gain insights from what is actually getting learned, what is the robot doing, can you reliably deploy this robot in this particular setting or not? You as the engineer or the scientist or even the user might not be able to have these confidences associated with your models. So the other argument to make is, let's say somehow we address all of these limitations and people are able to truly show that scaling is sufficient, right? Scaling just works. You can just train these large models and they will solve all of robotics. Let's say that's true for a second. Even if that is true, my argument is they might not be necessary. Just because it's sufficient, that doesn't mean that's the only way to do it or that's even the best way to do it. So my argument is that they might not necessarily be, they might not be necessary. So we have to be thinking about alternate pathways to getting to the kind of autonomy we want from robots. There are, of course, tons of ethical considerations that I'm not even talking about, right? Of course, you can always ask the question of who's going to have access to now? Who's going to be able to have access to the compute that's required to train on these data? Even if you're fine-tuning, it takes a lot of compute to fine-tune. Right. So these are also considerations that we have to take into account. So let me now talk about what tends to be our approach to solving these problems. And one thing, of course, I want to specify here is, of course, it's not like it's only our lab works on these kinds of problems. There are lots of people who do really cool work from very similar lens. The idea, I like to think of this as structured methods that are striking a careful balance between two ends of the spectrum. Think of a spectrum where one end is analytical and design methods. These are methods we have been studying for decades. We know exactly how they work, and you can write theorems about it, right? So you know exactly what to expect. But the issue tends to be that you can't quite apply them everywhere. They tend to have very small margins of applicability. So generalization tends to be an issue. On the other hand, you can think of learning from scratch, where these are the typical end-to-end methods that require a lot of resources, but they tend to have really complex behaviors that emerge out of these systems. The core focus tends to be very much on the emergence aspect of it. How much can the robot learn by itself without having the human provide any kind of biases to it, right? If you think of these as two ends of the spectrum, structured learning is what lies in the middle of that spectrum, or in the middle region of that spectrum, right? So a few examples of structured learning could be, you can design your policy architecture because you know something about your domain, you know something about your task. You can design your state and action spaces similarly. You can limit your hypothesis space of general parameters, whatever you want to learn, even if it's the same general, let's say, multi-layer perceptron, you can limit your hypothesis space because some constraints on that hypothesis space gives you certain kinds of guarantees that you care about. You can think about constraining the output of the model, or even having modular designs where you have a complex problem you're trying to solve. For some of those components, you know exactly how to design them and they will work generally, but there are some aspects where designing becomes very difficult, and or even if it's possible, it's highly limiting. You can replace those models alone with learning. So essentially, the whole idea here is to only deploy learning when necessary, and only deploy learning when we know that the alternative solution could be cumbersome for whatever reason, right? So there are three core design principles that we follow when we design these kinds of structured approaches. One is efficiency. Efficiency both in terms of samples, efficiency also in terms of computation. The second one is expert-free. What I mean by that is not that an expert is not designing these methods, but it doesn't take an expert to use these methods. Our focus is, it's okay if we have to spend a whole semester in our lab trying to figure out the perfect model architecture. But as far as when deployed, the architecture generalizes to the class that we care about. And if people are able to use it readily without having to tune hyperparameters, we consider that expert. So that's exactly what I mean by that. The third one is predictability. What can you say something about? This can sometimes look like guarantees. Some of our work and methods come with strong theoretical guarantees, but not always. But even when they don't, do they have enough transparency so that you know what sort of reasoning is happening under the hood and you can say something about what's happening? So it's like I mentioned, these are just examples of what these things entail and what are the different core principles that are guiding our design. So today's focus, I'm going to focus squarely on manipulation as a case study, because I want to give you a general flavor of the types of methods we use instead of just giving you a listing of all the things we have done. So let's take manipulation as a core example. And I'm going to introduce some of the structured methods we have introduced in this space to help learn a variety of manipulation skills across different robot morphologies and complexities. So what are the underlying structures that we are going to explore? Specifically, what exactly are these structures, right? So in the talk is titled New Wine in an Old Bottle, but the old bottle is the kind of the structure that I'm talking about. But what are these old bottles that I'm talking about? So there are going to be three old bottles that we're going to use. One is many of our methods are heavily grounded in dynamical systems theory. We borrow a lot of tools from dynamical systems theory in order to model these kinds of problems. And I will, in a second, get into what exactly that means. We also rely on topological properties because oftentimes when you parameterize things as dynamical systems and you're trying to learn robot skills, it's very helpful to think beyond the Euclidean space. So we take topological structure into account. And third one is modularity. Modularity in the sense that we have, of course, any particular problem requires different components. And we are going to we will look at examples where some of these components are manually designed, some of them are learned. And even if different components are learned, some can be shared across tasks and so on, so that you can expedite skill transfer, for example. So why specifically these structures? Of course, there are a million other ways to model things and learn things. So the first thing that I say about this is we take this approach because we tend to see desired movements as just shortest spans on some complex manifold. So all the skills that we are trying to learn for manipulation, for example, can be thought of as there is a desired way in which you want your robot to react, right? Think of it as a dynamical system that says, you're here, you need to go here next. This is the general policy that you're trying to learn. This is essentially a rollout of a dynamical system. But the ideal dynamics that are governing these kinds of behaviors can be in complex manifolds. So you can think of them as shortest paths in those manifolds, then it becomes a problem of identifying the manifold and then being able to just learn the dynamics on that manifold. The second thing is that robot states and action spaces tend to have inherent geometric properties and topological properties. So this lets you exploit those properties as well, because these don't have to necessarily be just fictitious topologies and manifolds. You can also incorporate the inherent topologies that are present in a robotic system. The third one is learning global patterns from local example is possible when you learn things like manifolds and dynamics from manifolds, because just with local examples, if you have regularity assumptions that hold for a task, you can now generalize much more beyond than your training set. Even though your training set is contained only in part of your state space, this is a much better way to extrapolate, essentially. It's a highly structured way to extrapolate what you're learning from your training set to a larger set and learn some global patterns. And most importantly, we have well-established tools to introspect the system. So what I mean by that is once you learn these systems, they tend to be structured enough that there are existing tools that you can deploy to analyze what will happen to the system as you roll it out. Can you show that there is convergence property? Can you show that if there is stability issues, so on and so forth? There was a question. Yes.
Yes, I originally asked topology in what space?
So yeah, so a couple of things. So topology can be either in the inherent configuration space of the robot, because many robots have inherent topological structures in their configuration spaces. But you can also think about topological spaces and manifolds in fictitious spaces, because like I mentioned, we are thinking of these dynamical systems as governing equations that are generating desired motions of robots. So this is not directly tied to your Euler-Lagrange dynamics, for example. These are just reference trajectories that you're generating. And one of the ways in which to think about this is there is an abstract dynamical system that's generating these kinds of trajectories, and you're trying to learn it, right? We would, of course, have to then rely on a lower level control that will enable those motions or enact those motions on your robot. Of course, the other thing that I'm not getting into here, but will be obvious in some of the slides, is we, of course, take into account some of the limitations of the fact that you have a real system on which this should be deployed. And those things will also influence the kinds of topology and kinds of manifolds you're learning. But so to summarize, some of the manifolds are in inherently defined configuration spaces of the robots. Some of the manifolds are in completely fictitious spaces in the sense that they don't follow the properties of the inherent robot dynamics. And finally, complexity can emerge from simpler solutions. This is the idea of primitives, right? Think of it as motion primitives. If you have complex motions, you can sequence simpler movements together or compose simpler movements together to get something more complex out of it. So let me start with something that we did a very long time ago. This was back in 2017 when I was a PhD student. That got me started in this line of work. We were very curious about how to design dynamical systems as these behavioral dynamical systems for which we can say some properties, like we want convergence properties, strong convergence properties. We want to be able to reject disturbances and so on. We started looking into contraction analysis. So contraction analysis is a way to analyze dynamical systems, and it specifically tries to analyze incremental stability. And what that means is your ability to exponentially forget your initial conditions. Despite two trajectories starting further away from each other, how quickly do they converge to each other is what's called the contraction rate. And in many systems, especially the ones we were looking at, were goal-directed motions. You know for a fact that wherever you start, you want to end there. And it's just that you take a specific path to end there. And what we found was that you can enforce this constraint while learning your model. This was a very simple Gaussian mixture model, and we enforced these contraction constraints on it. But of course, one other thing that I have to mention here is your system might not always converge in the Euclidean space, in the sense that the trajectories might not get close to each other in the Euclidean space, but they will in some other manifold. So you can simultaneously learn the metric that defines the manifold, as well as what is the dynamics on that manifold. And together, we were able to show that you can learn complex motions with these kinds of guarantees. So, but what is the point of doing this for robotics and manipulation? Turns out you can do a couple of very simple serial link arm manipulation problems with guarantees and robustness. For example, this is a windowless basement in Connecticut where I am bothering a robot trying to do a pick and place task. And you can see that the robot is able to keep coming back and to its end goal despite my perturbations. These are actually just automatic effects of the way in which we parameterize and learn these models. This robustness was not added to the policy. This was just an inherent property of the policy. The second one is that you can also adapt to things like sudden target changes. Maybe you want to, I move the cup, but the robot knows that that's where I need to pour the water. So it's able to adapt naturally to the new location. So then I moved to Georgia Tech, and this was work when I was a postdoc there. So Asif here and Archie, so they wanted to take the power of neural networks and see if we can learn more complex tasks. And more particularly, what we were interested in, what if we still have serial link manipulators, but we cared about motion and desired motion on multiple parts of the robot? Because sometimes you don't just care about moving your end in a particular way. You also care about how to keep your elbows, right? How to keep your wrists. Sometimes force constraints come up. And of course, you have to worry about obstacle avoidance of your whole robot. So they figured out a way to take essentially the kinematic tree of the robot and have it be systematically combined at different nodes here. You see on the kinematic tree, each of them can be either a manually defined policy for a particular point on the robot, or it can be a learned policy. And whenever you are learning policies, we are still learning a manifold on which the desired behavior is a geodesic. And this is just a systematic way of combining these different policies. And they were able to show that you get these nice flexible and responsive systems that can do tasks. For example, in this video, Asif is trying to create perturbations as the robot is trying to reach for something inside the cupboard and then close the cupboard, for example, right? So you can get these kinds of more complex behaviors as opposed to just end effector pick in place. So you naturally get these constrained motions, and you can define multiple task spaces, and you can also naturally incorporate obstacle avoidance into this mix. So then Mandy, who was a PhD student who recently graduated, she had this idea of, let's add even more structure to this. So the previous work was called Riemannian motion primitives, and we were learning those motion primitives. Then, so we wanted to see if we can learn what are called geometric fabrics. So this was in collaboration with folks at NVIDIA. So Mandy's idea was, what if we move away from Riemannian geometry to Finsler geometry? So Finsler geometry is just a fancy way of saying your metric doesn't just depend on state, but your position, but also depends on your velocity. It's a very counterintuitive topic. It's like if I go from Philly to Atlanta, it's one cost, but if I come from Atlanta to Philly, it's a different cost, right? But in higher dimensional spaces and complex settings, this extra flexibility offers even more expressivity. And you can have things like homogeneousness in degree 2. You can learn the geometries of your nominal behavior, and you can have a more expressive way to combine these multiple task spaces together. One nice theoretical set of results that came out of this is that when we did the Riemannian motion policies, once we combine these different task spaces, they could be conflicting with each other. So we sort of lost the theoretical guarantee of convergence when we came up with that method. Although in practice, that was not a problem, we couldn't write a theorem that said that it will converge. But with neural geometric fabrics, with the added structure to it, we were able to show that you can now maintain the theoretical properties of convergence, but also a couple of other nice properties emerged out of it. So neural geometric fabrics are path consistent. What that means is you can learn a skill, and then you can just tune a knob for how fast you want to execute the skill. So the speed at which the robot is moving will not affect the desired trajectory that it's taking, which tends to be very helpful for a variety of tasks. You can now modulate how quickly you're doing the same task. And you don't have to learn the task at all, again, or you don't have to learn any additional policies. You can literally just change the speed of the rollup, right? We also were able to do conflict-free policy blending, which is just a fancy way of saying you have these different task spaces, how to incentivize the learning in those task spaces simultaneously such that they don't learn opposing things for a given task. For example, you don't want your elbow to want to move in a completely different direction and your wrist to move in a completely different direction. How do you seamlessly integrate them is what this board does. And more interestingly, we were able to do this completely in the joint space, which means that you don't need to have someone expertly design operational space controller, which anyone who has done before knows how annoying it is to design very good operational space controllers after you have learned the skill just in the task space. So let me give you an intuition of what's happening under the hood of geometric fabrics. So you can think of there is an underlying manifold on which I was talking about the desired movements that are happening. So you're learning two things at once. You're learning just this manifold first. This manifold is telling you what are the general nominal behaviors, right? If I place a ball here, how will it generally move is what you're looking at, right? Just with this manifold, you can think of this as like a system that doesn't have any friction or energy, it's just free flowing. So it just keeps moving, right? On that manifold, following the local curvature of the manifold. But you can also bend and shape this manifold, which is part of what you learn in your neurogeometric fabrics, but you can also add energy to it. So which means that you are allowed to push on that direction faster or slower. So we call that energization. So learning these specific mass matrices and fictitious and geometric forces helps you simultaneously learn the shape of the manifold that governs this ideal movement, but also helps you modulate the speed at which you're moving. So these parameterizations were directly baked into the learning method so that you will learn only these parameters as opposed to one network that generates your actions based on your current state. So we deployed this on a more complex system of a multi-fingered hand along with the KUKA arm. So I think this was combined 23 degrees of freedom system. And we were able to show that across different tasks, we were able to learn very effectively how to perform a variety of dexterous manipulation tasks with the multi-fingered hand. Well, the entire 23-dot system is controlled by that NGF. So once again, because the one nice thing again here is you don't need operational space control. So you are directly joining in the joint space, which is particularly useful when you're working with hands. Because if you have a parallel jaw gripper and a serial link manipulator, perhaps you can learn in the task space and expect that relatively simple operational space control will get you the performance you want. But if you really want to learn multi-fingered hands, it would be next to impossible to just define something in the task space. So we were able to directly learn policies in the joint space. And we also compared it, of course, with a variety of different methods. And what we were particularly interested in is seeing how sample efficient is this structure, right? Because we are adding all these structures. One could always argue, what if you didn't have any of this? You add the same amount of data you're learning from. Let's just learn with a neural network. So it turns out, if you add all of this structure, you get significantly better or significant improvements in your sample efficiency. So these are just curves that are showing you right from a completely unstructured model, let's say a neural network, a large enough neural network with the kind of expressivity you want, how many demonstrations it takes to learn the kinds of things you want, and how the imitation error and the success rate. And we also tracked safe deployment rate because we wanted to deploy it on hardware. Of course, we wanted to make sure the trajectories are safe before we roll them out. So we also computed how many of them are safe to deploy. And we consistently noticed that with smaller amount of samples, you are able to learn better as you add more and more structure to it. So this is the Riemannian motion policies that we talked about. Turns out, of course, if you have something like an LSTM, the fact that these are first order Markov models is actually limiting for you. So if you add LSTM, that makes things better for you, but you get even more improvements as you get better and better, right? So, and this is just with imitation error. It somewhat correlates with success rate, but not completely. So you can also see a wide amount of difference, for example, between the LSTM model and the models that we have. So the orange one you're seeing is just the geometric fabric on your end effector, essentially just the hand, and you just use a classic method for your arm. So you see even benefits with just doing that, but you can combine the whole system and learn it with these neural geometric fabrics. So right after this project, we were curious about how do we leverage prior learning? Because one thing we noticed was when we started working with complex different objects, let's say we are doing in-hand manipulation, which tends to be even more hard to learn. We started wondering, it turns out that when we learn from a given data set, some objects you're able to do really well. And this is true even for if you're doing completely reinforcement learning. And for some objects, it tends to be very difficult, right? This is actually a result from a different group that did in-hand reorientation, and they reported these success rates. You can see this sort of categorization of like, there are some objects that are more spherical that tend to be pretty easy to manipulate in hand. And then there are some objects that are very hard to manipulate. What we wanted to find out is that, can we leverage the structures we have been building to see if somehow what we are able to learn here helps with the problem here, as opposed to learning a separate model for just these hard policies or for these hard tasks or hard situations. So Mandy came up with this idea of, let's say we want to learn skills across different objects. What if we had made an assumption that there is some common shared skill across these manipulation tasks that we can capture with our neural geometric fabrics, and then have a specific parameter of the neural geometric fabric that just gets modulated by a higher level policy. And that's the only policy you will learn for the new task. Essentially, the idea is we are going to learn from easy tasks, which are more, they are easier to learn by definition, they have better sample efficiency. But what you extract from that is this low level skill. And the hope was that, can this translate now to a harder skill where you don't learn the policy from scratch? All you do is just learn your high level policy for the new task. It's essentially like there is some underlying structure of how you want to be moving for a given task, in this case, in-hand reorientation. But for different objects, you need to guide those dynamics in a specific way. And it turns out that's exactly what helps. You can see that here, this low-level structure is fixed. So the low-level skill is fixed for you. You get a reward, so you can learn this through RL, but all you're doing through RL is learning the high-level policy. You are not changing anything about your low-level policy. You're keeping it as frozen, right? So you're now significantly reduced the number of parameters you have to learn. You have significantly simplified the learning problem. And turns out this gives you really good improvements, once again, in sample efficiency. Here, what we are comparing is, we have 4 different versions of hierarchical models, which have the same structure that I talked about. The only difference is that, what is the parameterization or the structure of the low-level policy? So the same idea of doing this hierarchical, higher level and low level, but for lower level, you can either use NGF, RMP, NDP is neural dynamic primitives, and then you can use just a simple MLP. But you can also compare it against, what if you just warm start, which is a common idea in RL for skill transfer. You just warm start the policy, and then you fine tune on the new task. And the third one is, what if you learn from scratch in reinforcement learning? As you can see, it significantly benefits then you are able to exploit structure. In fact, we saw that the more structure you had for your low-level policy, the better the sample efficiency was. And another interesting thing is that warm starting might actually be hurtful for you. Because in this particular case, we were trying to learn from easy objects, the common skills, and then transfer them to hard objects, which are essentially narrower, which require slightly different ways to manipulate. Turns out, if you take an RL policy that was trained on the easy objects, and then directly fine-tune it on the hard objects, it actually is worse than learning from scratch. So you sort of plateau because you're stuck at a local minima that you're not quite able to escape. So we were able to see that the more structure we add, the better your sample efficiency tends to be. The curve on the right is essentially that we were also counting the number of consecutive successes, because we were dealing with an evaluation protocol that we were continuously changing the desired orientation of the object. And we wanted to see for how many consecutive sequences will the policy succeed, which essentially speaks to its consistency. We also tried to see what exactly is getting learned at the low level. So one nice thing of this architecture is that you can visualize what the policy is trying to do at the low level that's shared across tasks. Turns out, if you combine high level and low level, it's able to effectively manipulate and reorient objects, especially even objects out of distribution for you, because of course you have learned. That's not quite true, because of course you're fine-tuning the high level policy, but you're able to do it well. But if you only use the low level policy, it doesn't quite work, but somehow this is helping. But if you notice carefully, it has somehow learned that the low level skill is all about just moving the object around, maybe without a goal. Right? It doesn't have a goal orientation that it's conditioned on. It doesn't have a direction to get to, but it has learned that, oh, this is how I sort of can manipulate and move my object around. And just having that bias helps with the skill transfer. And we are able to see that it translates when you combine it with a high level policy, it's able to guide low level policy, which has learned this intuitive skill that irrespective of the object, I sort of have to bounce the object around like this a little bit and move. This was uncovered by the low level policy, and the high level policy is just so essentially guiding this low level policy. This question, sorry.
The learning is impressive, but what do you store?
Not sure I understand. We essentially store just the policies themselves. So the shared policy, which is the neural geometric fabrics, is something we store, of course. It's a parameterization, it's a set of parameterization and a policy architecture. We store that. And the high level policy is another RL policy that we are learning on top of it, which does not have any structure. It's because it's a much smaller network, just predicting particular parameters of the low level policy. So at the end of the day, when you roll out these policies, you are storing two policies. One is the high level policy and one is the low level policy. If I misunderstood the question, I would love to clarify. Okay, so the next thing we wanted to explore along these dynamics was, so far we have looked at structures with dynamical systems where we said there is a complex nonlinear dynamics that underlies all of this motion. So let's try to inject as much structure as possible to learn what exactly those nonlinear dynamics are. But one thing that we kept bumping up against is that as we added these more structures, we continuously saw that, oh, our expressivity and our ability to learn complexes increased, but computation costs also started going up, right? Even if you don't have really large models, even if you don't have really large amount of data that you're relying on, it's still the model architecture got more and more and more complex. Yes.
Sorry, just a follow-up to the previous question. Rujna asks, do you store kinematic configurations of the hand, the contact points of the hand, and object trajectories?
So we do not make any assumptions about the object. What we are tracking here is just the 6-dot force of the object. We are assuming we have access to the 6-dot force of the object, so we can condition the policy on. So we have a little bit of history we condition the policy on. So essentially you have to store like maybe the last few samples of your object. And we are directly predicting reference targets in the configuration space of the hand, which means that if this is a 24-dot, I think, right hand, so we are directly predicting what would be the 24 degrees of freedom. And there is a little bit of history there again, which is a few more samples from the past, essentially to circumvent this first order Markov assumption. So you have some context on which you're depending your policy, but those are the only things we store. So, like I was saying, the models were getting fairly complex and the computation costs were starting to go up because we were trying to learn more and more complex nonlinear dynamics. So then Yunhai here, who's my PhD student currently in the lab, he wanted to try to see what if we use Kuban operator theory. So of course, why would one want to use Kuban operator theory? Turns out Kuban operator theory is a very efficient way of learning highly nonlinear dynamics as linear dynamical systems. It does this by the idea of doing lifting. So for some of you, or for whoever is familiar with the kernel trick in machine learning, you can think of Kuban operator theory as like kernel trick, but for dynamical systems. The idea is to lift your original dynamics to a higher dimensional space in which it's approximately linear. The original idea is from 1930, I think, and the paper proposed this idea, but of course it assumed infinite lifting, right? It's essentially the same as like your universal approximation theorem. It says any arbitrarily nonlinear dynamics can be now learned as a linear system if you have infinite dimensional lifting. But of course, that's not quite practical. It sort of fell out of favor. But more recently, in the last decade or so, it has really found a resurgence. There is a lot more work on Kuban operator theory now that we have better compute and data, more importantly, that we can collect, right? So he wanted to test if we can use Kuban operator theory to learn dexterous manipulation skills. So here the idea was, you take your states that you typically care about, right? You're still learning behavioral dynamics. You're at a current state in your configuration space. You want to decide what to do next. You will condition it on your current configuration, maybe some history, and also your object states. What if you lift this to a high dimensional space, and then once you do that, you have a linear system, which means you can do literally least squares on it, right? You can solve the learning problem amounts to a least squares problem. But of course, the tricky part often is that people will complain about Kuban because sometimes defining the lifting function is the trickiest part of the Kuban operator theory, or using Kuban operator theory. So we wanted to start with something very simple. So we said, what if we just use second order polynomials? You only lift up to second order polynomial. So you essentially take your inputs, you pass it through first order polynomial, some cross terms, and up to second order polynomial, and you use that to form the basis basically. And you lift the states, and you literally just do least squares on your demonstrations. And the next day he comes to my office and says it works. And I was very skeptical, and he kept trying to rerun the experiments, and it kept working. And the worst part was it worked across different tasks without tuning the polynomial lifting functions. We were very surprised, but turns out that's all it takes. So for a complex set of tasks like doing text manipulation, like in-hand reorientation, door opening, and things like this, we were able to see that just with polynomial lifting, you are able to learn linear dynamics. And that ends up generating reference trajectories that are good enough so that you can just deploy it using a PD controller at the end of the day. So we evaluated this across different methods, but let me give you a better intuition for what's happening under the hood. So let's say these are the dynamics that you care about, right? These are some complex nonlinear dynamics, or this is the solution to some complex nonlinear dynamics that you really want to capture. But what Koopman does is it takes this through a lifting function and projects it onto a space where this is essentially a much higher dimension than the original space, where the dynamics will appear linear. So what it's essentially doing is that you lift your original states to your new state, your lifted states. In Koopman operator theory literature, it's often called observables. And the evolution of observables is linear. So you just have a matrix that gets multiplied to this one, so you can predict the next one. So of course, you have to decode to get your original states. The way we design our system is there are, of course, a couple of tricks here, right, to make this work. The trick is still generalizes across the board. The trick is, one, because text manipulation is object-centric, you can't just learn behavioral dynamics just on the configuration space of the robot. You have to keep track of what your object is doing as well. So we simultaneously learn the joint dynamics of what the object should do, as well as what the robot should do. So that's why you see both the object state as well as the robot state here. You lift them together, but another trick that we do is we actually, once we lift it to a higher dimensional space, we just append the original states to the higher dimensional space. And then we learn linear evolution. The reason why you would do this is you can have a decoder pre-design. You don't have to learn a decoder specifically to extract your original states from your lifted states. You can just directly pull them off from a linear transform because they are part of your lifted states now. Of course, this slightly limits your expressivity, but turns out that doesn't really seem to affect the problem, or in this particular domain, that doesn't seem to be an issue. And then what we did was, once we learned the reference dynamics, we also wanted to see if we can learn the inverse dynamics controller directly from the data that we have, instead of having to, because we found that you have to manually tune the PID controller for each task. And we wanted to see if we can learn the controller as well, so that nobody had to directly tune. So when you deploy this, you don't need an export to tune your PID controllers as well. Question?
So what you described about including the original states in the observables, like I'm guessing that sort of just amounts to a certain choice of projection from your higher dimensional space. So like, is there any sort of additional like that seems like a particular choice, and like I'm just curious what like other choices you could make and like what costs might come to make.
Yeah. So the other choice is you don't append, you only lift, and then you learn a linear dynamics in the lifted space. So here's what would happen after you've learned it, right? You still will have a least squares problem. You can recover a linear dynamical system that describes the evolution of your observables or this lifted space. But when it comes time for deployment, the robot still needs to know what should happen in its configuration space. The only way you can go from here to there is you have two options. One is you design your lifting functions in a way that it's invertible naturally. So what I was describing is just one class of such lifting functions. You can define other classes of lifting functions that are also invertible analytically, so that you can extract it back. The other thing you could do is you could lift it arbitrarily. You can even learn a neural network to lift it, but you would have to learn a decoder simultaneously as well. Without that, you won't be able to extract your original states back. So those are sort of the pros and cons. We did this because this is the simplest thing one could do. And turns out that was sufficient to get this to work. Thanks.
I have a question about
Yes.
the lifting functions of these. How do you ensure that like the polynomials that you use to lift from, let's say, from the original space to the lifted space yield a linear system in that lifted space? I think because that's one of the issues with what you mentioned right now. Like there's a lot of papers that do this with neural networks where they learn the decoder, they learn the encoder, one neural network for the encoder, one neural network for the decoder, and then, or they try to do some bijective neural network learning. And they're you need to force the linear, the lifted space to be linear, right? Like to follow this linear evolution. So how do you do that with these polynomials? Like, do you need to do some sort of tuning of figuring out like what's the order of the polynomial in order for your lifted space to be linear and to follow this linear evolution?
So
how do you do that?
The short answer is if you're manually designing this, the only way you can do this is by trying something and see if it works. The only other way to not do this at all is to learn that end to end.
Yeah.
Right. It's not end to end in the traditional sense, but you're learning it along with your linear dynamics. It's just that in this particular domain and a problem, we used second order polynomials, and that was sufficient, and we never tuned it. That was literally the first thing we tried. And that was sufficient to capture the nonlinearity that's present in the system. So what that's telling us is that, I mean, we also tried third and first to see what happens. And third didn't really improve performance. It basically was the same thing. It just took slightly a few more seconds to learn. And first didn't learn, of course. So because there was not sufficient nonlinearity, so it was not learning anything. So if you're manually designing it, what you're essentially doing is you're defining a set of basis functions, and you're approximating your dynamics to those basis functions. So it's not that you're somehow ensuring that the true dynamics are linear in this space, because we don't even know what those true dynamics are. The only thing that you're worried about is how well does my assumed model approximate the data that I have? And since we are doing least squares, that is the optimal model given that parameterization. So when we have situations where that's not possible, or your definitions of very simple polynomials are not sufficient, that's when you have to learn a parameterization, a lifting function that will take you to a system. And when you do that end to end, you are simultaneously conditioned to be linear. So the linearity is enforced, contributing to your representation learning, and the representation learning is contributing to the linear system that you're fitting.
Do you have any intuition why it worked, like the second order polynomial?
So that's because I think what we are learning, the key here is, so this is something I was going to talk about at the end anyway. In all of our works, the major disadvantage is we don't do representation learning at all. In all of our works, we assume we know what the state space is. Here we assume we know what are all the objects you should pay attention to. We know this is the object you have to pay attention to. We have a 6-stop post for it. We need to pay attention to this nail. We need to pay attention to this hand and the configuration space. Given all of that specified for you, the dynamics are not very non-smooth. They are pretty smooth dynamics. If you roll out the individual trajectories, you would see that it's not very non-smooth. So it's relatively easy to capture that just with the polynomial basis. But the moment you have high dimensional states where you don't quite know what your representation is, you will run into trouble, right? If you do this in image space, for example, there's no way it's going to work with the polynomial, right? You would have to learn either a compact representation, which you can then lift, or you have to simultaneously learn the lifting function as well. So yeah, once again, we compared it with our existing methods, including some of our own from the past. And what we saw was that, here's what I want you to pay attention. So the top one essentially is showing you for across different tasks, how much time it took to train the policies. So the orange curve is what the Koopman operator-based method takes. As you increase the number of demonstration, of course, all the methods take longer to learn because you have more data to parse. Of course, it gets better with task success rate and so on. You can see how ridiculously small the number of seconds it takes to learn this, because all you're doing, once again, is just learning a least squares, right? You're just doing least squares fitting, and it tends to be significantly more efficient compared to other methods. Of course, this is not just least squares, there's also the inverse dynamics controller that we are learning, but even put together, it doesn't take significantly long time to be able to learn these kinds of skills. And we see this across different tasks and across different number of demonstrations. One thing we see is that even across performance, we're able to match some of the best performing methods from the literature, which includes the neural geometric fabrics that I talked about. It, of course, performs really well, but it comes at the cost of taking longer to train. Of course, it's still better than an unstructured neural network that is learning the policy, but it still takes longer. And more importantly, if you notice the scalability, you can see that you can now start passing more and more data with less compute compared to other methods, which will start taking more and more time to train. So the next thing I want to talk about is, what if we want to learn from state-only observations? So this line of work was motivated because Yunhai finished that project and he wanted to see, what if we don't have access to demonstrations? Having access to demonstrations seems a little costly, which essentially says that you have state action pairs, right? Or essentially you know everything about the torque values as well as your states. So for example, that's what we use to learn the inverse dynamics controller. But what if you don't have access to it? A common motivating example is, let's say you want to learn to play soccer, right? So, and you want some videos from Christian Ronaldo, right? You want to learn to play soccer from. What do you really do from it, right? If you want to learn, you will watch videos, right? And then you will learn from that. You can potentially learn to make these kinds of shots with nothing but just the video and yourself and being able to practice, right? So this is the idea that we were trying to replicate for dexterous manipulation. But without action labels, let me talk about what tends to be difficult first. So if you don't have action labels, what happens is that, let's say you perfectly imitate what the demonstrator is doing. You are able to perfectly imitate, this is the kind of motion that they're exhibiting, I'm going to do the same thing. For example, let me do two things. So in this run, I picked up the object successfully. And in the next run, I did this, but the object never came back, right? I have no way of knowing what's the contact force. I have no way of knowing what exactly, how amount of pressure I need to apply. But my motion of just my hand was near identical in both of those cases. So this is because if you only have access to states, which is just your configuration space, it's not sufficient to fully capture a skill. And this is particularly true for prehensile manipulation. We also looked at what happens in non-prehensile manipulation. This problem is much less pervasive in non-prehensile manipulation. You can get away with not having action labels much more. In fact, even for in-hand reorientation, you are able to do it without action labels as well, right? Of course, the performance drops a little bit, but we found that it doesn't drop significantly. But for prehensile manipulation, it significantly drops if you don't have access to action labels. So it leads to failures. So if you come back to the intuition of what you would do, you would probably do two things. One is you would watch your videos and then have a mental model of how to perform the same kind of movement, right? You're going to watch an expert do something, and then you're going to try to see, oh, I'm going to try to do the same thing. You're building a mental model of what that motion is. But of course, you wouldn't stop there and assume that you now know how to execute that. You will have to practice, right? You will go to the field and practice very similar kicks to see if you can sort of emulate what the person is doing. So this is what we call motion imitation versus motion emulation. In motion imitation, you're purely interested in copying your expert, right? You're trying to replicate as much as the expert's movement as possible. In emulation, the focus slightly changes. When you practice, you're probably paying way more attention to what's happening to the ball than you're paying attention to what's happening to your leg. So we take a very similar idea and we came up with a two-stage framework that we call CIMA, which is combining imitation and emulation for motion refinement. The first part of CIMA is identical to the Koopman operator-based idea that I talked about. So notice when you learn just the reference dynamics without an inverse dynamics controller, you don't need to have action labels. You just need state rollouts. So you're learning this generation policy, and that is essentially a Koopman-based dynamical system that can now give you ideas of what you should do at any given state, right? So we call this motion prior. And once again, of course, we pay attention to both what happens to the robot as well as what happens to the object. We are simultaneously learning the interdependent motions. And the second stage is the emulation stage. Here is where we employ RL, but what we do is we freeze this generation policy and we learn a refinement policy that is only learning to make local adjustments to your motion prior. As opposed to learn something from scratch, you are essentially starting with a motion prior, and then you're refining the policy. So based on either in a reality or in simulator. Of course, we don't have physical results yet. We are still running those experiments. These are simulated results from the simulator. So you're using a simulator to learn the reinforcement learning policy, which is the refining the motion prior that you get. A key component of there are two key components of this map. One is it's intervention free. What I mean by intervention free is that we only rely on action free observation. There are some prior works that learn from state only observations that rely on experts providing what they call in-domain or teleoperated demonstration to compensate for the fact that you don't have action label information in your larger data set. So they collect a few in-domain expert demonstration to compensate for that fact. This framework doesn't require it. The other advantage of this framework is that it's task agnostic. What I mean by that is we have a specific way in which we design the reward function, which is a task agnostic reward function. We don't design different reward functions for different tasks. The key here is, once again, emulation. What we define the reward function as is, what can the robot do such that it reenacts the motion that it learned from the object that it learned from the expert. So notice how the lack of action information is only giving you problems when it comes to how to move your hand. What happens to the object is unambiguously demonstrated by the expert. You know the point was to pick this up, right? So if I do something and I ask you to do the same, you are definitely paying attention to the object. And from just my observations, you know exactly what is happening because there's no actuation of the object. The object just moves in a particular way. So we use the tracking reward of the object from our reference dynamics to be able to design the reward function. So it's task agnostic in the sense that for a different task, we never touch this. We in fact never touch the framework at all. For different tasks, only the data changes, nothing else changes, right? So we were able to come up with this intervention-free as well as task-agnostic framework to combine imitation and emulation so that you can learn from state-of-the-art observations. So this is what the policy architecture looks like inside them. So you have your initial states, you get your Koopman policy to generate a bunch of desired motion priors for your hand state and your object states. And then this is your motion prior that goes into your refinement policy. But your refinement policy is also going to take into account some contextual information. For example, it's going to take into account what are my current observations, because it needs to be able to adapt, right? There might be disturbances that are happening while you're doing manipulation, so you have to be cognizant of that. You also take into account what were my previous PD targets that were generated. So this is the history I was talking about. So you take these into account. So you adjust your motion prior based on your context to produce what should be your next reference state for your hand, right? So, and that gets given to the robot so that it can execute the task and you can run this closely. So we wanted to compare and see how much does this really benefit in practice. So we tried to take these three prehensile manipulation tasks and we compared it against two things first. One is we compared it against what if we assume we have the expert's movement. So there is no question of how accurately you're learning the motion. We just assume literally having access to the expert and the same initial conditions. We just roll it up. And then we use just a PD controller to track it. Turns out you don't do very well for most tasks if you literally try to accurately track the expert's motion, because there are finer adjustments that you can never perceive that are what are making the difference between success and failure when it comes to prehensile manipulation. And then we have another baseline where we learn the motion prior from a Koopman-based dynamics and then use a PD controller. Once again, you don't do very well. Any slight increase you see here, you should just discard it as noise. It's not like it's somehow magically learning to be more robust here. This is just the luck, fluke. I'm sure it won't even repeat if we run this again. But here's where something that will repeat. So in Cymer, of course, the cost you're paying, there's no free lunch. The cost you're paying is you now have extra cycles in your simulator that you have to run. You have to practice essentially. The practice is the cost, but it's able to substantially improve your performance on these tasks. And the structure really helps you do this. So we also try to see what sort of intuitive changes are happening under the hood. Why is this successful? What sort of adjustments are happening under the hood? Turns out if you take object relocation, for example, and you try to measure the grasping force exerted by the hand, you notice that after adjustments on all fingers across the board, when it's doing something like a power grasp, the hand is learning, the refinement policy is learning that I need to exert a little more force. If you look at actually the PD target, some of them are slightly inside the object so that you will exert enough force to hold on to the object. So it's learning to refine its motions and apply more pressure for a firmer grip. If you look at this hammer task where you're doing a tool use, you're picking up a hammer and driving a nail down, what you're seeing is that once again, your contact force increases, but not just that, your motion is also adjusted such that you are hitting the center of the nail more as opposed to slightly on the edge of the nail, even if your expert data was a little bit noisy. Because for these tasks, remember, the expert data, actually, I didn't talk about this, it comes from an expert RL policy that was just trained for a very long time, which also had access to demonstrations. So that policy, of course, is not perfect. It's going to have some defects and some slight problems. So it's learning that those kinds of things need to be fine-tuned. And what I'm comparing here is essentially the distribution before refinement and after refinement. And you can see this here. Similarly, for the door opening, it learns that if you create a larger movement, right, a larger rotation, and create more momentum when you're making contact with the door to swing it open, it helps you generate more force and open the door. So it's learning to twist the hand a little bit more compared to what the reference trajectory was telling. So we also try to see, what if we just take the things that we learned here? Let's say the object relocation task. You learned what to do with a ball. You practiced it with a ball, basically. Now can you zero-shot generalize to a variety of different tasks from the, let's say, the YCD data set? Turns out it has a pretty impressive zero-shot generalization. Of course, not to all the tasks, not all the objects, but to many, many of the objects. In fact, there are many objects for which it's outperforming the expert policy. That's because it has this nice hierarchical structure that has a very sensible motion prior that gets refined, as opposed to directly predicting your desired trajectories from just your state. This added structure really helps with zero-shot generalization. Of course, the other baselines that are pure RL or soil completely fail when it comes to different, completely new objects because they're totally out of distribution. But these the Cymer is able to exhibit pretty impressive performance when it comes to zero-shot generalization to a variety of objects. There are some objects here where it fails completely. That's because our hypothesis right now is that they tend to have very different geometry than the object you're trained on. The more complex geometry you have, the harder it seems to be for the policy to adapt. That's because the way in which you have to refine your motions might completely change for different objects. Maybe the way in which you have refined your motions for, let's say, taking something like a mustard bottle might be so drastically different if you're dealing with a power tree, because even your grasping strategy might be different. So you can't just try to adjust the previous strategy you learned. Let's say you learned a power grasp for a particular object. There's no way you're going to make local adjustments to it and turn it into a pinch grasp. Right? That's too far from your motion path. So we suspect some of that could be because of that. The refinements take longer and you need larger refinements to be able to learn. So let me conclude by talking a little bit about what sort of things we are very excited about. So we have been pushing this envelope on trying to do dexterous manipulation with these highly structured models. But some of the things we have not done yet that I'm very excited about is to be able to do model-based learning and control. So instead of thinking of all the structure I talked about that we can use to learn behavioral dynamics or reference trajectories, you can think of it as what if we learn forward models for the robot, in the sense that your ability to predict what will happen next to your object and your robot if you apply a certain action. If you have such a model that's based on open operators and has a linear structure to it, you might be able to easily leverage tools like model predictive control or even model-based RL for that matter. So the other thing that we are doing is doing structured skill transfer and composition. So what I mean by structured skill transfer and composition is the other thing that you can do when you have a coupon-based policy, you can do what are called dynamic mode decompositions. They are essentially going to give you different modes of your dynamics. And my hunch is many tasks would probably share certain modes. So you don't need to relearn your modes. So potentially you can learn the library of these dynamic modes that for a new task, you just learn how to combine them together, as opposed to learn the dynamic or the dynamics from scratch. We are also interested in doing self-play because when you want to do model-based learning, we have found that if you just collect randomly sampled data, it doesn't quite work. It fails often, or even if it works, it takes a very large amount of data set, like a really large data set to learn even simple policies. But if you have self-play, which tells you even simple things like, if you're trying to learn a model, you know for a fact, like for example, you know just moving around above the object is not going to reveal anything about your interaction with the objects. So taking those kinds of things into account and doing guided self-play is one thing we are looking into. Post-hoc inspection and certification of the learned policies, once again, leverage the fact that we have these structures, so we can at the very least analyze these structures, if not condition and constrain these structures so that you can get guarantees out of this. So you can do guarantee by design. We are also interested in doing representation learning. This was, we just talked about this in a bit. So far in none of these algorithms we are doing representation learning. We are assuming it's given to us, but that's also a very real difficult problem because some expert has to define something and potentially for different tasks, different representations are better for you. So being able to learn a representation, especially across multiple sensing modalities, would be highly effective. And we are also trying to extend this to see if we can handle deformable objects or bimanual manipulation. So what I want to do next is thank the students who did this work and also my collaborators who have been instrumental in making all of this happen. I just get to brag about them, but much of their efforts were necessary to make this a reality. And I want to conclude by saying that if you really take into account highly structured ways in which you architect your policies, your learning algorithms, and take existing knowledge seriously and inject them into your learning frameworks, you can significantly improve efficiency, autonomy, and predictability of robot learning. Right. So I didn't have time to cover another section of work where we apply the same kinds of ideas for multi-agent coordination, but that's also something that we do in the lab. So if you're interested, you can check out the lab website. Thank you. I'll stop.
So we're running very short on time. I'll take one question before we, okay, maybe two questions and then we'll end for the day.
So in your neural geometric fabric work, right? So what exactly are you learning? You're learning a metric for a manifold and also a correction term.
Yeah, in excitation for the for your dynamics as well.
Okay, so what role does the correction term actually play?
So there are a couple of things that are possible. So one is shaping the manifold itself.
Right.
So you can think of it as what is the right direction in which to move.
Right.
So that's being shaped by the manifold itself. So your shaping function is essentially learning that,
Right.
so that at any given point in that manifold, you know what to do next. And the other thing, the forcing is essentially learning sort of the speed that I was talking about. The path consistency comes from the manifold itself, but you're adapted, so you can sort of decide how fast to move, how to energize your system. Because if you don't have any energizing of the system, actually the robot won't move at all, it just stays still. So you have to add this external energy so that the motion will happen in that landscape. So you're learning how to energize the system simultaneously.
Right, okay. Have you thought about like how to incorporate, let's say, disturbances or those kind of things on?
So-
it's in this framework, because it seems like you're able to capture very complex.
So it depends on what you mean by disturbances. There are one kind of disturbances that are effectively you get for rejection, you get it for free, which is essentially if you have intermittent perturbations, you get almost free robustness out of it because you have a time invariant system. You know at any given point what to do next.
Right.
It's almost like somebody kidnapped you and put you in a different part of the state space,
Mm.
but you always know your dynamics will tell you what to do next from that place.
Right.
So sometimes this kind of robustness is not enough for some tasks. I don't have a good answer for that. But if you have other types of disturbances in mind, I'm not sure.
Right.
I had a quick follow-up question about like his question on the manifold.
Mm.
So you had a very nice slide where you showed, for example, one trajectory that's shaping your manifold, right? What is it that you're learning about them? Is it the metric itself that you're learning on the
Yeah,
manifold?
you done the
Okay.
metric, yeah.
Because sometimes, I mean, I've seen lots of works that they focus on metric learning, like from particular trajectories. And the metric is very accurate near the data, but the metric starts degrading as you get far away from the data.
Right.
So I wonder, which that breaks all of the stability and convergence assumptions. Like if your metric is shaky when it goes, or it becomes indefinite or something like that when
Yeah.
you go further away. So do you handle that?
Yes, so that
Okay.
we don't directly learn a matrix that defines the metric.
Okay.
We instead have this structure that defines the metric and only learns parameters. So there are, even in our RMP work, we do technically under the hood, we do a Chomsky decomposition.
Okay.
And only learn the factorized matrix
Okay.
instead of the full matrix. So by definition, the system will never predict a indefinite matrix.
Yeah.
So we have those kinds of structures in place to prevent that.
Mhm.
But one thing I would acknowledge is outside your training data, you just have this extrapolation of this local knowledge of geometry.
Mhm.
There might be ideal geometry on the other side of your training set that is very different from what you see here.
Yeah.
You will never learn that, right? That's almost impossible to know unless you have
Unless
data.
you have data from
Exactly.
that
But one thing
side,
we
yeah.
can make sure is we don't lose stability guarantees because it will always be positive definite, the
Yeah.
metric. So you will keep your convergence properties. It will just extrapolate this local geometry to your global state space. And the hope is that your training data captures that kind of geometry that you want.
Mhm.
It's entirely possible you can construct very specific numerical examples where this is not true,
Mhm.
and you just will obviously naively think it's the same geometry there when it's not. But the only way to know is if you have data in that part of the state space.
But for example, like in a very simple example where, let's say you're doing this local extrapolation of the geometry and so you enforce it to be identity when you're super far away from your data. And that will bring you back theoretically on the manifold, but you don't know if that's actually feasible for the robot to follow, right? Like, because you're not really considering like the actual geometry, it's just like an extrapolation
Yep.
of the
Yep,
geometry, so you
exactly.
don't know, right? Like, I
Yeah.
mean, you just hope that it'll be good, but you don't really know.
Yeah, that's
Yeah.
absolutely right. You're just hoping that that's a decent enough job. So the only thing that you will get out of it is you will come back
Yeah.
to this converging point. You will, because it's
Yeah.
global convergence. But how you get there is tricky,
Mhm.
right? It's unclear.
All right, please join me in thanking Dr. Ravichandar.